Hello everyone. The magnetorheological fluid and as well as the electrorheological fluids. These two fluids was invented somewhere in 1940s. The magnetorheological fluid was invented by a person called Rainbow, which has been invented somewhere in 1948, and the concepts with respect to the concept with respect to the electrorheological fluid came existence in somewhere around 1980s. But as these two fields are what we can say it has been matured, or where the technology has been implemented with respect to the application came into existence somewhere in the end of the what we can say the 19th century. Now here in this what we are discussing is with respect to the Bingham's plastic and as well as the related models. Now one might expect the formation of the fibrils with the ER or the MR fluids would increases the fluid's viscosity, but the fact the slope of the shear stress versus the shear strain curve rate, thus the viscosity is changes a little if at all. See, this it is common with respect to either it may be the MR fluids or it may be the ER fluids. As we know that the fluid is dispersed, or what we can say it has been dissolved with a magnetic particles, or what we can say the polarized particles. These polarized particles or the magnetic particles will energize and form a chain like structure when the electric field or the magnetic field is applied. As you know that the shear stress versus the shear strain curves will also start increasing it. Once if the loading takes place, automatically the shearing strain will also starts increasing. The effect of the fibrils is instead to produce a shear stress that is largely independent of the shear strain rates. This is commonly referred as the yield stress, which is denoted by or which is represented by the tau. Adding this term, the Newtonian model results into a Bingham's plastic model, which has the stress strain relations. Now here in this case, the strength with respect to the what we can say the field increase in field, either it may be the magnetic field or it may be the electric field with respect to the either the magnetorheological fluids or with respect to the electrorheological fluids. Once if the field starts increasing it, automatically the viscosity will also starts increasing it. It means that the shear stress and as well as the shear strain will be something like a linear. See, the repeated cyclic loading, if it continues, and the same thing if it is for a smaller duration, then also what we can say the polarization effect, it will be retained in the particle, and automatically the viscosity of the fluid or with the oils may increases. Once if the viscosity starts increasing it, and even there also what we can say the shear stress and as well as the shear strain will also starts increasing it. Now the what we can say the Bingham's plastic model equation can be represented as tau is equal to tau of F plus eta into nu dot. Now here where the equation F is the strength of the applied electric or it may be the magnetic field. In the case of the electric field, it is being represented as a E. In the case of the magnetic field, it is represented by means of the F. The yield stress of the field strength, generally dynamic viscosity, the tau versus the nu curve is determine these lines. The shear stress axis is taken as a value of the yield stress tau ys. In case of the data measured a small strain rate, the line deviates from the idealization as shown in the figure. Initiating the motion or the flow requires to overcome the static yield stress, the tau ys, which is often larger than the dynamic value tau yd, which is as shown in the figure by the dashed path, which has been represented in the next slide. Once the tau is reached to a dynamic value, it tends to flow like a straight line towards the tau y, and the nu start decreases. This may be due to the friction between the moving parts or the seals, etc. And this deviation from the ideal behavior is given a small enough that it may be ignored. See, this is what we can say the comparison between the dynamic shear stress and as well as the static shear stress. Now here the straight line indicates the what we can say the static, and the what we can say the curved path which has been formed over the straight line is with respect to the dynamic. Now the pre-yield response of the what we can say the material it is varying as the time elapses. According to the Bingham's plastic model, the stress less than the yield stress tau ys produces a no flow or the ER or the MR fluids, but in reality the fluid naturally responds to the stress in this range, and for many purposes it may be regarded as the viscoelastic solid. The figure shows a typical stress strain characteristics of the ER or the MR fluid loaded up to the beyond yield. The yield occurs at approximately the same strain nu regardless the field strength. When the tau ys increases with the field as discussed above, for a clarity we have shown that the yield strain as corresponding to the peak stresses and the each curve, but the particles and the correct definition of the yield for these materials is not so clear. The onset of the nonlinearity in the storage modulus is an accurate indicator of the yield, and that of the correlated well with the measure of the static yield stresses. Now here in this case, in the case of the material, once if it starts loading, the shear stiffness of a viscoelastic solids including the unyielded ER and as well as MR fluids, it is often represented by a complex shear model. G star is equal to G dash plus J into G double dash, where the real part G dash is called as the storage modulus and the measure of the material ability to the elastically stored strain energy, while the imaginary part G double dash is termed as the loss modulus and the associated with the dispersion of the energy during the deformation. The loss factor is defined as the ratio of the loss modulus to the storage modulus, which is nothing but G double dash by G dash, and the same can be determined by measuring the phase difference between the strain wave input to the material and resulting the stress wave. A predominantly elastic material will exhibits a small phase difference and a very small loss factor, typically less than 0.1. The viscosity of the material and the phase difference will approaches 90 degree, and the corresponding losses factors will be quite large. See, as here in the case of the what we can say any viscoelastic material that is especially oils which is mixed with magnetic particles, or it may be the polarizing particles. These particles is under repeated uses the what we can say the MR fluid or it may be the ER fluid viscosity will starts increasing it. Once if the viscosity starts increasing it even without the application of the field, either it may be the electric field or it may be the magnetic field, even these the particles will behave and arrange it like something like what we can see in the chain form. because of that what we can say, instead of the tau starting from the zero or at the origin, it starts from somewhere little above. It means that the load bearing capacity and also the yielding capacity of the material will increases. This property is a what we can say a major disadvantage for the ER, or it may be the magnetorheological fluids. See, the major phenomena of the particles is it should not behave like what we can say in a linear fashion in a chained form even after removing the electric field, or it may be a magnetic field. If it behaving like something like a what we can say in the chained form only, then automatically the material will loses its property